Hey, it's Mr. Shrum, and we're going to look at metals, nonmetals, and metalloids. Let me share that. All right. So in the periodic table, these are some of the first or most abundant types of elements. The modern periodic table arranges elements by atomic number into 7 rows and 18 columns. Each element is identified by a lettered symbol placed in a box or tag with information about the elements. The atomic number typically appears at the top of the box. So we have an activity, and it explores the periodic table and looks specifically at one simple way to categorize elements. For now, we'll skip that and then just talk about the metals, the nonmetals, and metalloids. Metals, you're probably familiar with many of the properties of metals. Clean metals have a shiny metallic luster. They also conduct electricity and heat. For example, electricity travels easily through copper wire because electrons pass readily from one metal atom to another. So that's why anything dealing with electricity, there's a lot of copper being used. You can experience the heat conducting property of metals by touching the hood of a car. On a hot day, the metal hood conducts heat quickly to your hand. So the hood feels much warmer than a non-metallic object. Likewise, the hood feels cooler than non-metallic objects on cold days because the metal quickly conducts heat away from your hand as well. Except for mercury, the silver liquid found in thermometers, all metals are solid at room temperature. Solid metals are typically hard, although some, such as the alkali metals, can be cut with a knife. Most metals are malleable, meaning they can be hammered into shapes or rolled into sheets and into useful shapes and stuff like that. They are also ductile, so you can stretch them into wire. The chemical properties of metals vary widely. Metals such as platinum or gold are fairly non-reactive and don't rust or tarnish easily. Other metals react quickly with oxygen or even the moisture in the air. Here's an example of King Tut's gold death mask, and it's remained untarnished for centuries. So they haven't had to restore it as much as you would if it were made out of another type of metal. Nonmetals, every day we interact with familiar nonmetal compounds in mixtures like glass, wood, and stone. Nonmetal elements play an even more critical role in our lives. For example, the elements oxygen and nitrogen are the primary components of the air we breathe. Nonmetal elements are not malleable or ductile. They don't possess metallic luster like metals do, and most are poor conductors of heat and electricity. Nonmetals such as helium exist as a gas composed of single atoms. Other nonmetals like fluorine exist as gases composed of diatomic molecules in which two atoms are bonded together. Helium is extremely non-reactive, while element fluorine reacts with many elements, including other fluorine molecules. The states of nonmetal elements vary. For example, elemental bromine is a liquid at room temperature, while other nonmetals like sulfur are soft solids. Sulfur crumbles when hammered, but diamond, one form of solid carbon, is the hardest natural substance known. So in these example pictures, we have matches. they contain a phosphorus top, and that's why they're so easy to spark. Diamonds are made of carbon and then refined to this pretty state. Metalloids or semi-metals. Metalloids exhibit properties between those of metals and nonmetals, and corresponding to their location between the metals and nonmetals in the periodic table. Metalloids tend to behave as nonmetals in many ways, but they show some electrical conductivity, which is a characteristic of metals. Rather than being electrical conductors, several of the metalloids, silicon and germanium in particular, are semiconductors. Semiconductors don't transfer electrical charges as well as conductors, but they do it better than insulators, which don't conduct any significant current at all. Silicon is the primary element used in making semiconductor wafers for integrated circuits, computer chips, and solar cells. Fortunately, this important element is abundant on Earth. Silicon dioxide, commonly known as silica, is the most common mineral in Earth's crust. Sand is mostly composed of silica. And here's an example. A microcircuit board or microchip, things along those lines, are made of silicon. And next section is element groups. Element groups. There are a lot of ways to slice up the periodic table. Here it's divided into three major sections. We have elements in group 1A through 8A, and those are known as main group elements. Elements in the B groups, so right here, this middle section, the B group, at the center of the periodic table are known as the transition metals. The final group, intertransition metals, this pink section. So intertransitional metals, sometimes they're called the lanthanides and the actinides, and they fit into the main body of the periodic table, but they're usually pulled out to conserve space. Because if you put that in the middle, the periodic table will stretch a very long ways, and it makes it a little harder to read, but it's not too difficult, honestly. And it has the periodic table tool here, and you can click on groups and select each group we just discussed: main group, transition metals, and intertransition metals, lanthanides and actinides, to highlight them on the periodic table. So let's do that. Ta-da! So periods 1. Oh, sorry, those are periods, not the groups. So we can do lanthanides, actinides, and these would fit between these, if that makes sense. So all of these would fit right in between these transition metals, and the whole table would stretch further. But we can group 1A, group 2A. We have which would be here. Let me show you. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. You see how those are numbered a certain way? Well, this numbers it the other way. So you can think of these as 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So 13 is 3A, and then 18 is 8A. So anything after, just don't get too confused about that. And then we have all the metals. You can see the nonmetals over here. And you have the lanthanides, the actinides. You can look at S block, P block, D block, F block. Yeah, and that's another reason why they are separated the way they are. Oh, weird. Okay, I didn't click on that button before. I don't know if these are all that helpful pictures, but hey, it's kind of neat. Anyway, moving on. So we're going to look at the main group families, 1A and 2A right now. And yeah, I'll just play the video first. Actually, let me make sure I'm sharing the sound. Yeah. Okay, we're good. Turn on the captions, subtitles, and go.
Group 1 of the periodic table is a group of reactive metals. Lithium, sodium, and potassium are at the top. These metals are so reactive they have to be stored under oil and need to be handled with care. Lithium is so soft it can be cut with a knife. You can see how shiny the freshly cut surface is, but leave it exposed to the air for a few seconds and it quickly begins to tarnish. It's reacting with the air. This is sodium. It's even easier to cut, and again the shiny surface soon discolors. Potassium is even softer and reacts so quickly it tarnishes immediately. Another way of comparing reactivity is to place the metals in water. Lithium floats. It reacts immediately, fizzing and skating around on the water, which is evidence that a gas is being produced. By carefully putting a tiny amount into a boiling tube, the gas can be tested with a lit splint. A squeaky pop means it's hydrogen. Universal indicator shows that at the end of the reaction, the solution is alkaline. Lithium reacts with water to form lithium hydroxide and hydrogen. So how does sodium react? Again, it floats on the water and fizzes. The gas produced is hydrogen. And the solution is alkaline. When sodium reacts with water, sodium hydroxide and hydrogen are formed. Sodium is more reactive than lithium. It's below lithium in the periodic table. Potassium is below sodium. So how do you expect potassium to behave? Potassium is definitely more reactive than sodium and lithium. It reacts immediately, and the hydrogen produced ignites on its own. Universal indicator goes blue. Potassium reacts with water to form potassium hydroxide and hydrogen. Rubidium and cesium are elements which lie below potassium in the periodic table. How would you expect rubidium and cesium to react with water?
All right, so you see how combining experiments and predictions from the table, you can predict what is going to happen. Among the main group elements, the elements in group 1A at the left of the periodic table, excluding hydrogen, are known as the alkali metals, highly reactive elements, and they tend to form oxygen-containing compounds that dissolve in water to produce solutions that are strongly alkaline or basic on the pH scale. The group 2A elements are also metals that form alkaline oxygen compounds. However, group 2A elements don't dissolve in water as readily as group 1A elements. As a result, they're often found in earthy soil deposits and are called the alkaline earth metals. So that's why earth metals is sometimes used for 2A. Okay, so now we're going to look at 7A and 8A, which are the last two groups. On the right side of the periodic table, we have the 7A group, or halogens. These are highly reactive elements and are often found combined with other elements as salts. So salts can be from the left-hand side of the periodic table. In fact, the term halogen means salt former. For example, chlorine combines with sodium to form the compound sodium chloride, or common table salt. Located on the right edge of the table, the elements in group 8A are known as noble gases. These elements are chemically stable and are non-reactive. They tend to not gain or lose or share electrons easily because of their stable configurations. They have enough electrons and they're okay. And we'll learn more about that later. In the past, these elements were often called inert gases since they are almost completely non-reactive. And we can find the halogens here. So 7A will be 17 on this table. So here's the halogens. You got fluorine, oh, it didn't go back to the, whoops. So we have fluorine, chlorine, bromine, iodine, astatine, and tennessine. And so salts can be from this side of the table. Lithium, sodium, potassium, and they can react with these halogens over here. These guys are reactive, and these guys are reactive. These, the noble gases, are not reactive, not as reactive. They're okay with the electron configuration that they have. But these guys can react with these and form salts. Here, let me get back to the, there you go. Electron configuration. So elements in the same group have similar properties because of their highest energy electrons have similar configurations. This table shows the electron orbitals that define the highest energy levels for each element. So groups 1A and 2A are in the S block. The B groups, or the transition metals, are the D block. We have the main groups from 3A, 4A, 5A, 6A, 7A, 8A. We have the P blocks. So it goes from S block, P block. Remember that helium is also in the S block. That's the one weird thing about the organization of the periodic table. So it goes S, P, D, F. So S, P, D, F. And so you can look at that tool and then organize them based on the S blocks. So here's the S block. It includes alkali metals and alkaline earth metals. They are soft and reactive. And it also contains hydrogen and helium, which are nonmetals and gases. The elements of the S block have their valence electrons in S orbitals. And it can contain a maximum of 2 electrons in the valence shell. So that explains why the block is 2 columns wide. So you only got 1, 2, and then helium's just along for the ride. Then we have P block. They contain quite a variety of properties. It contains nonmetals, metalloids, and metals. Metalloids are a mix of metal properties and nonmetal properties. The P subshell can hold a maximum of 6 electrons in 3 distinct orbitals. So that's why we have 6 columns here. You can have 1, 2, 1, 2, 1, 2, 2, 4, 6, if that makes sense. And then you get your D block. So these are the transition metals. It contains metals that are typically hard and dense, good conductors of heat and electricity. They are less reactive than the S block, and they often form colored compounds. The D subshell can hold a maximum of 10 electrons in 5 distinct orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then finally the F block. So those are your inner transition metals or lanthanized actinides. These are all soft metals and many are radioactive. Most can be found naturally on Earth, but the actinides are typically made in nuclear reactors. So lanthanides can be found in nature. Let me see. These guys can be found in nature. Actinides are usually found in nuclear reactors, created in nuclear reactors, and found in nature. This F subshell can contain up to 14 electrons in 7 distinct orbitals. And for this activity, click Clear Filters to get started. Then look at the quick facts display for the noble gas elements, helium, neon, etc. Look specifically at their electron configuration. What is the same about each of these elements? Why do you think we put these elements in the P block? Okay, so clear filter. And then we're going to look at the noble gases. Electron configuration. We have 1s2 for helium. We have neon. Electron configuration, we have 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, and so on. So the main pattern you should be picking up on is this s2p6. So s2p6. The s orbitals are full and the p orbitals are full as well. Helium fills the 1 level completely, the 1s orbital. Neon fills the 2s and p levels completely. They all fill out the s block and the p levels of electron orbitals. And then do the same for group 1 on the left. What is the same about each of these elements? Well, if you do group 1, we have 1s1, 2s1, 3s1, 4s1, and so on. So lithium has only one electron in its highest energy level, 2s. Likewise, all the following alkali metals have only one electron in their highest energy level. Find boron, look at its electron configuration, then look at the electron configuration for the elements to its right, all the way through neon. These 6 elements are considered to be in the P block. Why do you suppose we classify them that way? So boron's right here. The configuration is 2s2, 2p1. Then we have 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5, and 2s2, 2p6. Their highest energy electron fall into the p orbital from 2p1 to 2p6. That's why we classify them that way. Each period in the periodic table represents the start of a new energy level that is being filled with electrons. As the atomic numbers increase, the elements have more protons and electrons. The shape of the periodic table reflects how the electrons fill the energy levels and the 4 types of energy levels, S, P, D, and F. Notice that the A group elements correspond with populating the S and P orbitals. Likewise, the transition metals correspond to filling D orbitals, and the inner transition metals correspond to filling F orbitals. The S, P, D, and F blocks simply reflect the electron structure of the elements. The S and P orbitals make up what is known as an element's valence shell and contain what are known as valence electrons. Valence electrons occupy an atom's highest energy level, moving from left to right in a period. As energy levels fill, more and more electrons are added to the valence shell until 2 electrons fill the s orbital and 6 electrons fill the p orbitals. The traditional group number on the periodic table equals the number of valence electrons in each element. The noble gases, group 8a, contain the maximum of 8 valence electrons, known as an octet. Okay, so the noble gases contain the maximum of 8 valence electrons, known as an octet. So you can see how this is organized. First, it fills up the S, and then if that's already filled up, 1s and 2s, then it moves to the P level, okay? So we're gonna drag each of the description below to the icon represents its proper location on the periodic table. Drag the items on the left to the correct location on the right. So look at these. This corresponds to group 1, group 2, metalloids, halogens, and noble gases. Okay. So filling d orbitals here, that fills up the green section. Excuse me. Group 1 has 1 valence electron, unlikely to react. Those will go in the noble gases. They're not likely to react. Metalloids, the triangles show where the metalloids are. So they're like between the metals and between the non-metals. 7a, we call those halogens. this next to last group, filling F orbitals here, that is this bottom purple section. Outer S orbital filled, nothing in the outer P. So that'll be group 2A, which is also alkaline earth metals. Halogens are those blue stars. Noble gases are the purple last column. Conducts electricity poorly. Well, no, I wouldn't say that. Group 1 reacts violently with water. The metals, alkaline metals. Transition metals, that'll be those green horizontal line or vertical lines. This group here. Inner transition metals, be those guys down here. And then metalloids, it says conducts electricity poorly. I don't agree with that. It just conducts less well than metals, but better than insulators. So I don't know if that's too accurate here. But that brings us to the summary. By now you should have a good idea why these scientists saw family patterns in the elements and why those patterns became more complicated past calcium, where the number of elements per period suddenly jumps from 8 to 18. Despite these complexities and others that the scientists encountered, their work still yielded a very useful tool. And for nearly 150 years, scientists have used the periodic table to predict properties for undiscovered elements. And they use it to consider ways to create new compounds and to make hypotheses about the unseen structure of the atom. Here are some other concepts and skills you should know after you're completing this lesson. Understand that the periodic table is organized in columns and rows by increasing atomic number. Be able to use the periodic table to identify an element as a metal, non-metal, or metalloid. Metals are on the left-hand side, non-metals are on the right, and metalloids are in between. The alkali metals, alkaline earth metals, transition metals, halogens, and noble gases, you should be able to find those. Understand that elements in the same group or family have the same number of valence electrons. So everyone in the same vertical group has the same number of electrons, valence electrons. You've also learned to use the periodic table and the chemical database tool, two powerful tools that you'll need from the rest of this course, for the rest of this course. And you can look at these other links. As a video, Livermore scientist team with Russia to discover element 118. So there's a lot of other stuff you can read about here. But that leaves us with a completed lesson. And if you have any questions about the periodic table, email me, message me, and I will try to help you out as much as possible. But until next time, have a good one, and I will see you all later. Bye-bye.